So essentially what we have here is a complete mirror of the BattleZip circuits. The one difference, I guess this uses MIMC sponge, but aside from the hash functions being different, the one difference is that this is hooked up to a front end. This is not yet hooked up to a front end or posting to smart contracts. So in the next month that will come, but otherwise, what we've done essentially is replicate the BattleZip's ZK Battleship game in the Halo 2 proving system. And what we have done, just look at the circuits here, we've got board, shot, board and shot. So we've almost perfectly replicated the idea that we've got these two setup proofs, board proofs that a user will use to demonstrate that they have created a valid board configuration and bind themselves to it without actually revealing that information to the counterparty, and then also using the shot proof to check hits or misses against that board commitment. So we've already talked about the shot circuit in a previous video. We've gone over the unit tests. We're going to consider the board circuit today, and we'll go into the code really quickly. So there's a lot of different moving parts, and we need to document it more for sure, but for the purpose of this, we're just going to talk about the synthesize step, which uses all of these chips except for a shot. Basically takes in 10 shot commitments, and then for each pair of two, that's a horizontal and vertical one, and it will apply the placement chip, as we actually produced a video documenting previously. That's actually really well documented how that works. Once it runs through that 5 different times on ships of length 5, 4, 3, 3, and 2, serialized by the input, basically like a tuple, you then will transpose all of those placements, individual ship placements, which have been checked for range constraints and stuff like that. You now transpose them, make sure that none of them collide with each other, as well as producing that final single field element that represents all of the placements in one board. So once we've got that transposed bitmap essentially of the placements, we compose it back into a single element, and then we hash that element. So finally we take that commitment, which is currently private advice, and we export it to the instance column, which makes it publicly available. And this full computation results in something where a individual or a user can input ships that represent their placement on a board, and so long as they're rational, following the rules, they can prove that their board configuration is valid, and they can create a binding commitment to it that they can share publicly. Ideally, what we have here is a way that you can provide a public receipt, that commitment, that can be used in future shot proofs to check against your board whether or not it hit, and then prove that you're using the same shot commitment. And this can be enforced at the smart contract level to establish truly trustless interactions. So the one problem that we have really quickly with our commitments, and it says right here to do, add signing here. There are less than 5 billion or less than 8 billion different pre-images that can possibly be used for a battleship game. So a weekend of hacking and easily break that. It's very insecure. And the reason is that hash functions are binding, but they're not blinding. So to get around this, what we were going to do was, in a way, salt this hash by signing the hash. Instead, what we could do is we could just do Pedersen commitments, which are very, very light, even compared to a Poseidon hash itself, where we are not only binding ourselves to a certain pre-image, but we're also blinding the commitment in such a way that you can't perform known ciphertext attacks. So for the purpose of the tests we're running, this is binding, not blinding. It's 80% of the way there, and it is actually what we shipped for BattleZipsV2, but given that this is A, the incorrect way to do it, and B, Pedersen hashes are much more efficient, we will come back and fix this before this is finally shipped as the full Halo 2 code. Okay, and here we can see all of the test cases passed. And very quickly, let's take a look at these test cases. So we have 2 valid board configurations, which eventually will have some ASCII showing the exact configuration, but valid board configuration, valid board configuration. And then we have all of these different cases of malicious inputs, essentially. So when it comes to the invalid placements, some of the measures that we took to allow the testing of all of this, one thing was that we used optional inputs. So it's possible for the board to accept 432 ships, which is not actually going to produce a valid proof. But we do want to test that that's the case. As well, we have a bunch of different and we can see this in the utils. We have a bunch of different options for different test cases, and we basically will manipulate the inputs according to how we want to test these cases. So that's all actually encoded here in this utility. It will, instead of having all of the placements be on one, it will mirror over a bit, so that it passes every other constraint but fails this dual placement one. There's non-consecutive, which will take a valid placement. So if it's 1111 for a battleship, it'll be 11101 and test that there's no actual valid ship placement. Extra bit will just randomly place a bit somewhere on a board. So if it has if it's a ship of length 5, you're going to get 6 bits on your board. Oversized does the same thing, except it makes the bit consecutive, and undersized removes that bit. It's a ship of 5, it'll be 4. And then we can apply those granularly to whatever ship we want. Place in each of these tests will target a different ship just for the purpose of demonstrating that it's not reliant on that first ship. So invalid placement, dual, non-consecutive, extra bit, oversized, undersized, these we've kind of already explained how they work. For each of them, they might be targeting a different thing again, but in general, these are crafted so that for each of these constraints, they're only throwing the expected constraints for this logic. They explicitly pass in inputs that will not throw any other constraints, so it's tailored very much. Besides that, we have invalid placement none, which again is an extension of no placement on an optional value. And so that will prove right here that it gets angry if you don't place something. Right here, the 2 cases where technically you do have consecutive bits that are placed. However, on, let's say, a destroyer ship, which is length 2, if you tried to place your ship on the very last bit, let's say on the 4th or 5th row on 49, and you tried to horizontally place at 49, it would wrap around to 50, and that would be encoded as the 49th and the 50th bit being set. And technically that would pass in all their other constraints, but we, as is shown in the placement chip, we explicitly synthesize the circuits in such a way that they don't even toggle the gates to allow that check. So we prove that in those cases where we are kind of placing something out of bounds for a specific row, either horizontally or vertically, that it will overflow. And then we check kind of the main logic that people expect, which would be collision in ships. During the transposition of all the ship commitments into a board commitment, it will take the 10 columns of 100 bits each, and it'll go row by row, checking if each has either 0 or 1 bits set. And when we're checking no transpose, essentially this is the base case where everything's horizontal and there's no serialization that occurs. If you were to print them all out as the witness itself, you would see the collisions there. However, with the transpose step, if you're placing your ship at, let's say, 3-4, you're going, and it's vertical, you're going to pass that in as 4-3. So immediately when you print it out, it won't appear to be colliding, but we want to check that that throws. And then finally, we test both if you try to provide the wrong advice, as well as if you try to provide the wrong instance value but provide the correct advice for the public board commitment. These actually throw the exact same constraints, so this might be redundant, but again, this just checks that if you take the Poseidon hash and add 1 to it, where if we look at valid, it's just Poseidon hash right here. This is going to fail its computation of the hash, so you can't lie about which board you're committing to publicly. It's binding, even though it's not blinding. And then we just check that permutation on the instance column as well. So moving forward, obviously we need to add Pedersen commitments at the circuit level to finalize the circuits themselves, at least for the privacy preservation circuits. And then from there, we also want to turn around and fully apply those circuits to the Web3 stack. So we want to do the same thing we did with the BattleZips Circom stack, where we have a front end and we have a smart contract that settles the proofs. So there's no reason that we can't use something like Zordle's integration as well as the Scroll snark aggregator for Halo 2 on-chain to post our proofs and settle them in a decentralized manner. Regarding ZK state channels, we are currently unable to accomplish the functionality that we need for kind of recursive state increments, which would be IVC recursion. It's just around the corner, and it's definitely, as soon as it does drop, we'll definitely be revisiting it in Halo 2. I think, if you look at something like Plonky 2, for instance, it's optimized to be a Validium, not necessarily a zero-knowledge proving scheme. So at the end of the day, Halo 2 would be the preferred mechanism or vehicle to do this, we believe. But for now, we are, once this last iteration is complete, we'll likely be investigating Plonky 2, as mentioned, as one way to accomplish recursive verification of the state incrementally, so that we can play entire games off-chain and verify them on-chain in a single transaction. Aztec Noir also has this functionality coming very soon, so as soon as that drops, we'll also be investigating the integration of Noir-based state channels. So as different proving schemes introduce IVC recursion, we will continue to prototype it in different languages until we kind of find the sweet spot. So again, the code can be found at github.com/battlezips/BattleZipsV2. We have the aforementioned fixes to make to our public commitment scheme for the board state, as well as adding the integration to the front end and to Solidity. But and we also want to, if we can find the means, produce much more thorough documentation, perhaps in the form of video series similar to the Circom documentation for BattleZips, something that goes over everything. But even still, this codebase is already very well documented. There's the BattleZips Discord, and largely we think this is already kind of good to go as a resource for new developers to pick up Halo 2.